Sharding is a very powerful technique. And like with any powerful technique, we have to understand where it's appropriate to use. And that means understanding what the benefits and what the drawbacks are to using the technique. So let's first start by talking about contention in a sharded system. Now remember, when we talked about Amdahl's law, we understood that contention has a dramatic impact on how a system scales. If we have a lot of contention in a system, then it limits our scalability quite a lot. Sharding doesn't eliminate contention. It doesn't make the contention magically go away. What it does do, though, is it isolates it, and we'll talk about how that impacts things. So, first question, though, is where does the contention exist? So within a single entity, we will still find contention. If you can imagine a system, for example, that is sharded by user ID, in that case, the contention exists within each user entity. Each user entity processes one message at a time, which means it's basically kind of like the photocopy machine where there's only one of them and you have a lineup of people waiting to use it. In this case, the photocopy machine is the user entity and the lineup of people is the messages going to that entity to be processed. The coordinator also represents a source of contention. So the coordinator has the job anytime a message comes in and we don't know the location of the shard, then we have to make a computation in order to determine that location so we can direct the message as appropriate. There's only one coordinator in the system, and so that represents a source of contention. However, a sharded system minimizes the contention, and the way that it does that is first off by limiting the amount of work that the coordinator actually does. So the coordinator actually has a very simple job. When a message comes in, it does a quick computation and then directs that message as appropriate. But there's optimizations on top of that. And so one optimization, for example, is if we've already made the computation in order to determine where that shard is located, then we don't do it again. We can just say, okay, last time I sent a message to this shard, I sent it over here, so I'll just send it over there again. And so we don't actually need the coordinator in cases where we've previously calculated where the shard is. So there's optimizations being applied there. So because the coordinator does very little work and because we have those optimizations in place, it's very unlikely that you'll ever build a system where the coordinator becomes any significant bottleneck. Entities, on the other hand, do represent a legitimate source of contention. They are a place where you might legitimately see contention in your system. However, it's isolated in this case. And so the way that it's isolated is, again, if we take a look at a system where we have sharded by user ID, in that case, our user ID or our user entity represents a source of contention. It can only process one message at a time. However, entities that are doing a lot of work, or users that are doing a lot of work, their entity will experience that contention and they will see the results of that contention. On the other hand, other users who are not doing a lot of work with the system, maybe just doing a little bit here and there, they won't experience contention because their entities aren't going to have those lineups. What that means is that you see contention in the places where somebody is legitimately taxing the system or putting load on the system. And where people are, just using the system casually and not putting a lot of load on it, you don't see contention. And that's really what we want. We want contention. We want these problems to be isolated to the problem users. We want the users who are putting load on the system to experience the problem rather than everybody experiencing the problem, whether they're putting load on the system or not. And so that's one of the big benefits of a sharded system, is the way that it isolates that contention. Now, how does this affect sharding, consistency, and scalability? Well, scalability is achieved by distributing shards over more machines. If we have 30 shards distributed across 3 machines, that means each machine is hosting 10 shards. Now, if those machines are being overloaded, what we can do is we can redistribute those 30 shards across, say, 4 machines, and now each machine only hosts 7 or 8 shards, and as a result, it has less work to do. And that's what we want, right? We want to be able to scale out and reduce the amount of work that each machine potentially has to do. So that's how we achieve scalability in a sharded system. Strong consistency is achieved by isolating operations to a specific entity. So Each entity exists in only one place. Each entity processes one message at a time. And that means that we can guarantee that first off, that entity will see every message, and it will see every message in a predefined order, in basically the order that it receives it. And so as a result, it can always come up with a consistent view of the world, and that view will always be the same when you talk to that entity. And so that's a powerful thing as well. Of course, it is important to remember that careful choice of shard keys is really critical to maintain good scalability, and we also need an appropriate number of shards. Again, if we only have 3 shards distributed across 3 nodes, then we don't have scalability. Scaling up is not going to help us. That's why we go back to that 10 times rule that we had suggested earlier. So how is sharding affected by the cap theorem? Well, sharding is primarily a consistency solution. Therefore, it sacrifices availability. If a shard goes down, there is a period of time where it's unavailable. Now, there's 2 types of cases where it could go down. One would be it's a graceful shutdown. Maybe we're redeploying a new version of the app, so we shut down the old one. If it's a graceful shutdown, then the system will buffer messages and deliver them once it comes back up. On the other hand, if the shutdown or if the disconnect is unexpected, maybe a system crashes, maybe there's a network failure, whatever the case, in that case, the rest of the system has no idea what happened, and so it can't buffer the messages because the shutdown was unexpected. It may have messages that are already in flight or whatever. So in that case, messages could potentially be lost. But really, that's no different than if you were just using a REST endpoint, for example, or an HTTP endpoint. In that case, you might send a message to a machine that you believed was there, only it turns out it's crashed in the meantime, and so your message doesn't get delivered. You get like a timeout or something like that. It's the same kind of idea. That message is now lost, and you have to take steps in order to recover it. Now, the shard will migrate to another node eventually. How long that takes depends on the techniques and the configuration that you are using with your sharding. If you are using techniques to manually notify the notify the cluster that there is a problem, that basically means that somebody has to log in and say this node is no longer available. In that case, that's going to depend on how long it takes somebody to manually log in. So that could be hours, days, whatever. There are automated techniques, though, that will speed this up dramatically. So the Lightbend split brain resolver would be the one that I would recommend. And what that will do is it will monitor your cluster, and it will recognize automatically when nodes are lost, and they will be shut down for you and removed from the cluster. And in that case, it can very quickly recover. So now instead of minutes, hours, days, we're talking more like on the order of seconds. In order for it to recover. So that's probably your best option, is using something like the Lightbend split brain resolver. Now, I mentioned at the beginning talking about sharding that one of the benefits of sharding is that it reduces the back and forth traffic that you have with your database. So how does that work? Well, it works using caching. And caching, if you've ever worked with distributed systems, can become problematic in a distributed system. And the reason it becomes problematic is because you might have multiple nodes which all have to host that cache because you have multiple nodes in a cluster, and they're all talking to the database. And now you get this problem where, first off, you have to keep your cache and your database in sync. You have to make sure that everything that's in your database is also in your cache. But then on top of that, that cache exists on multiple nodes in the cluster, which means you have to keep those caches in sync because you might get requests coming into the system and you don't know which node they're going to go to. So you have to ensure that those caches are in sync. And now we're back to a distributed system problem. Keeping those caches in sync isn't really possible in a distributed system. So what do we do in that case? Well, sharding solves this problem. And the way that it solves this problem is essentially making each cache unique to the entity. The entity maintains an internal view of the state of that entity in memory, and that internal view is unique to only that entity. It's not shared anywhere, so it's not a distributed system problem. There is only one copy of that cache. Now, what we do is we have something like if our cancel reservation message comes in, for example, our reservation entity will handle that, and it will update the cache and write to the database. Now, what order that happens in, that depends on implementation, but the point is it won't move on to another message until both have completed, which means by the time we get to the next message, we know that the cache and the database are up to date with each other. Usually what you probably want to do is to update the database and then update the cache, because that way if there's a failure and you have to recover that entity, then you know that it will be able to recover it from the database. So that's usually the way you do that. But regardless, we can guarantee that when the next message comes in, the cache and the database are in sync. In the meantime, we know that the cache doesn't exist anywhere else. It's only in this one place. That means that when a simple read request comes in, we can just use the cache. We don't actually have to go to the database because we know the cache is completely in sync with the database. So we just read the data straight out of the cache. As a result, our operations can basically become write only. They only ever write to the database. They never have to read from the database. The only time they would read from the database is if there's a failure or something like that, and we have to recover that entity into memory and therefore rebuild that cached state. Otherwise, we only ever write to the database. The result of this, remember, most applications tend to be read heavy, which means that this becomes a very, very efficient system because it's always reading straight from memory. It's almost never going to the database. So that can make it a very, very efficient system, and it can dramatically reduce the impact on your database and improve the overall performance of the system.